Okay, so let us start. So in the last class, I have given you a construction for the language cyclic shift of L when L is a context-free language. So it has a PDA. All strings accepted by L give some amount of cyclic shift. All strings that you form that way, that will be called the cyclic shift of L. And I claimed that if L is a PDA, cyclic shift of, L is a CFL, cyclic shift of L is a CFL. And I gave you a construction. Of course, it requires to prove formally that this construction works. But I start with an example. Okay. Consider this PDA for the A power n, B power n language. Okay, the standard push of A and then pop of A against every B. And eventually, if the bottom marker is exposed, when the input end of input is reached, it is popped and the acceptance is by empty stack and also by final state. Okay, so whatever. This state need not be a final state if you only want acceptance by empty stack, so it doesn't matter really. Okay, so if the input is A, B, 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 it is going to be accepted. And let us look at a cyclic shift of it. Maybe I start from here, A, triple B, double A. So this is my X. This is my Y. So this is X. This is Y. So let us see how our PDA for the cyclic shift language works. So it starts first by replacing this by adding some kind of separator symbol like this. Okay. Also, what it does, it chooses a state S or T non-deterministically of the original machine. So let us say it chooses the state S. So that is the correct thing to do because A's are still remaining. So S. So this S is remembered in the finite control, and this is the configuration of the stack after introducing the separator symbol. Then it sees an A. Okay. And this machine should push a capital A corresponding to this A. Okay, let me do one thing. Let me number these A's. Okay, so these numbers are actually, I would say, for your understanding. Actually, these numbers are not present. Only capital A is present. So this A matches with this B. This A matches with this B, and this A matches with this B. Right? Correspondingly, I will call this capital as A1, A2, A3, but anyway, this 1, 2, 3 are actually absent. This is just for your understanding. So what I will do, consume this first A. Okay, so in this case, so this will be 3, 3, 2, 1, 1, 2. Okay. So first, what this machine does, it pushes an A, because the original machine also does the same thing. So A, and what is this A number? This is 3. Okay, so there is no symbol called A3, only A is pushed. I am just printing this 3 for your understanding. Okay, continues to stay in this state S. Then this machine makes an epsilon transition. So this also guesses the same thing, makes an epsilon transition, goes to state T without consuming anything from the input. A, the third A is still there. This steps, state only changes from S to T. Okay. Then it sees a B, the third B. And this A is already there. So it simulates this step, replace that B by A. Okay, so here A is consumed, here B is consumed. So what remains is this.
Excuse me, sir.
Yeah, tell.
So like for pushing A in the first step, we
Yeah.
must write an additional condition like if the separator is...
Yeah, you do it. Yes, you have to update this transition slightly.
Yes, sir.
Okay. Then what happens? Then it sees the second B, B2. Okay. That requires an A to be present on the top of this stack, but nothing is there. Okay. So what it does, in order that it guesses some A, it should also remember that it has guessed that thing. So what it does, it replaces this lead by A, this, and then A again. What is this A? This is second B, so it should be 2. Okay. Okay, once again, let me mention that this 2, 3, 1, these things are not present. This is just for your understanding. Okay. So now it sees an A on the top of the stack, and since a B has to be consumed, B2, it can proceed. Okay. Then this B2, this is basically A3. Anyway, this was B3. Then B2 is consumed. B2 matches with A2. This becomes this. Okay. Then once again, another B comes, and this machine, in order to simulate this, will assume that another A is present on the top of the stack. And that turns out to be A1. Okay, so it guesses A. Mentally assume that this is 1. Separator A1, A2, then this. Okay. Then it can consume this B. Okay. And now the stack becomes this A1, A2, and this. Okay. That essentially completes the processing of this Y. Okay. Okay. So next, this X part has to be processed. Okay. So there are two possibilities. One is that, okay, and again, up to this point, the state is T. And then non-deterministically, it switches to this first part, state T. Okay. So S to T transition takes place, again, non-deterministically. Okay. Then two A's are remaining. Okay, so let me go to another slide. So simulation, what did I write there? Not S to T, T to S. Okay, so here also it is in state T. Okay. Then go to state T, sorry, S. And stack content was read A1, right? One was, yeah, A1, A2. And this. Okay. Next, what it does, it processes the first A. Okay. So there are two possibilities. In this machine, for every A, it can either push an A. Okay. But this machine behaves little differently because it has made an assumption that that capital A is already there. So it is now in the validation phase. Okay. So in the validation phase, it may proceed as like this, but in our example, it will not do so. What it will do, it will temporarily remove that lead. This is 1, 2. Okay. And then it sees that there is an A which is guessed previously. It will simply pop it out. And once again, bring back this separator. Okay. Then another validation should be there. A, the second so-called second A comes. So once again, removes this lead after consuming this, and it sees capital A. So instead of pushing a new capital A, it simply takes this out, pop out this, and replace the top by the separator. Okay. So you see that the gases are in correct order. That is why I have given this numbering, artificial numbering. 1, 1, 2, 2, 2. Okay. In order to illustrate that this is happening exactly in the correct order. Okay, now essentially the end of input is reached. So it will pop the separator out and eventually the bottom marker out, resulting in an empty stack. Convinced? The construction is now clear? Okay, so I suggest that you try try another example like palindromes or even Len palindromes. Or for that matter, you can convert equal number of A's and B's, that grammar, to a one-state PDA and do the construction on this, on your example. Okay. So here, because this is a very simple example, I always validated the guess, but it is also possible that instead of validating guesses, I do these real transitions. That is also an allowed possibility. Okay. So unless you look at other examples, you will not find. In any case, this PDA, like all other, can guess. And if there is a way for this machine to go from S to T or whatever, empty its stack, final state is not very important in this context. Then there is a sequence of guesses for this machine that will accept the cyclic shift and also conversely. So that requires a formal proof, but you go ahead with it. Okay, so let me know if you have further queries. So I leave it to exercise. Consider this S can be epsilon or ASB or BSA or SS. Convert this to a one-state PDA that accepts by empty stack. Okay. Although because of, I would say, this language is actually invariant under cyclic shifts, right? But anyway, so you do this construction on this converted PDA and see how it works. So, for example, if I have this A, B, B, A, B, and if the cyclic shift starts here, so this is my Y, this is my X. So in the validation phase, for this A and B, you do not follow the validation stage actually. Okay. Anyway, you work it out and find out how it works. Okay, so any more questions on this construction?
Sir, this construction has B as capital A. So capital A is a different or it is same as the small a?
Which capital S?
Capital A, sir.
Capital A, yeah. No, this is the stack symbol. Instead of small a, I am pushing capital A. I can push anything, U, V, W, whatever.
Okay, sir.
Okay. Okay. So there are lots of troubles in my machine today. Anyway, I can still continue. Okay, so that's about the previous week's leftover. Maybe let us solve one or two more exercises, new exercises. Okay, so let M be a PDA that never pops from its stack. And obviously, since it cannot empty its stack, it must accept by final state. Now prove that the language of M is regular. Give me an idea.
Sir, so we can make up an epsilon NFA with states from Q cross gamma, and such that the gamma represents the stack top symbol and Q is the state, and then we can plan the transitions accordingly.
Yeah, so that's it, right? So the input is M, which is Q, sigma, gamma, bottom marker, delta, S. I will construct an NFA or epsilon NFA. What are the things? Q prime, let's say. Sigma remains the same. Delta prime. Actually, we use capital delta, right? Okay. Anyway, it doesn't matter. S prime. F prime. So I want to convert this to this. Okay. So the idea is this. This machine never pops. So its working is governed by whatever it is consuming from the input, maybe epsilon, that is also allowed, and whatever is sitting on the top of this stack. Okay. Now, after this transition, okay, so what is meant by never pops from its stack? Maybe it means that I didn't write it clearly. Something new thing appears here. It may be that this A is replaced by something, but the stack size never decreases. So that is what I meant basically by never pops from the stack. Okay. So then I will have some symbol B on the top of the stack. And the next transition will be governed by this B and the new state and whatever it is consuming from the input. So the idea is that each transition replaces A by a fixed string, which is non-empty. Therefore, I never want to look back what is below this current stack top. Okay. So by looking at the top of the stack, I can always proceed. Okay. So I can take the states to be It can be Q, right? No problem. Same states. What should be S prime? No. Q prime, in Q prime, I should remember the stack top. Yes, I should do like this. Yeah, I have to remember the stack top as a state in the converted NFA or epsilon NFA n. So what should be S prime?
S comma bottom marker.
S comma bottom marker. And what will be the final states?
F cross gamma.
Yes, F cross gamma. Good. And delta prime. P A okay, will be the set of all Q B such that P A comma Q B some gamma is in delta, right? Now, because the step never decreases in size, this B is a well-defined thing. Gamma may be an empty string, and never popping means it replaces A by something at least one character long. Okay. So this B is well defined, and given the transition function delta, B can be found, and then I will make this transition without any problem, right? Yes or no?
Yes, sir.
Okay, so this construction is also clear. I have a few other exercises, but I think, okay, maybe I will continue up to 8:45. Then I will hand over to SK. Okay, prove that this language is a DCFL. Okay, actually, I would suggest I leave it to you. It's fairly straightforward. And you see that the PDA that we have designed for this language, so one state PDA. If A comes, this is exposed, a plus is pushed, A comes, plus is there, another plus is pushed, A comes, minus is there. Likewise, you have three transitions for B. Okay. And there is a unique thing to do for consuming each A. Right. So there is no ambiguity, or I would say there is no non-determinism here. But you tell me what should be, what is the difference? Okay, so maybe I write these things. Sorry, this is there. So this already a B is exposed to this, and if a plus is exposed, pop it out. I need another transition. What should that be? You tell me.
Epsilon bottom marker epsilon.
Epsilon bottom marker epsilon. That is what our earlier design did. But that was a non-deterministic machine, so it can guess the end of the input. Okay. This is a deterministic push-down automaton, so it does not have the capability of guessing. So how do I modify that? That is a guess, right? Fact that this bottom marker is exposed does not mean that the end of input is reached. But earlier PDA could guess because it's a non-deterministic machine, but now I am considering or constructing a deterministic push-down automaton. So what should it be?
So we can make another state and do an epsilon transition from if the bottom marker is exposed, and then keep that as a final state, and if more inputs are available, we come back.
Come back. Okay, so if you talk about comeback, then it sounds like possible. But never forget that when we design a DPDA, we always append some kind of end of string marker so that this machine does not have to guess. Agree or not?
Yes, sir.
Yes, sir, yes.
Okay. So whenever it sees that thing is happening, when it sees that and that is exposed, it will do this. Now there is no question of guessing. After this, what will happen?
Epsilon bottom marker epsilon.
Epsilon okay, fine.
Epsilon bottom marker some reject symbol are.
Reject symbol let us not introduce. Okay, there is a little bit of problem. Of course, we can do this, but I should have some final state. So maybe I convert it this way. This seems fine. Okay, so let me do this. If it sees the bottom marker, sorry, end of string marker, and sees that the bottom marker is exposed, it will go to the accept state. And there it will loop epsilon. Actually, this should be exposed, but I can call it star by star. So this is the accept state T. This is the start state. This is this direction. And if it reads this, so what will trigger this? Okay, so I have little space here to write. So what will trigger this?
The end of string is read, but there is some plus or minus.
You may keep it, do whatever. Okay, it will loop there. Now you see a completely deterministic push-down automaton and having a distinguished accept state and a distinguished reject state. Okay. So don't forget that a deterministic push-down automaton will have to consume this from the input before taking any decision. Okay. That's the only difference. Okay. Okay, so it's already 8:45. So I will tell you very briefly a very interesting result. So you know unambiguous grammars, right? Do you know or not?
Yes, sir.
Okay. So if a context-free language has an unambiguous grammar, it is called an unambiguous context-free language. Okay. So unambiguous. So this UCFL, unambiguous context-free language, they are defined by context-free grammars. On the other hand, deterministic context-free languages are defined by deterministic push-down automata. So this is defined by machines. And this is defined by grammars. Apparently, there is no way to use machine to define this class and grammars to define this class. And there is a relation. I am not asking you to prove this, that if a context-free language is deterministic context-free, then it is also unambiguous context-free. But this inclusion is proper. Okay. So I am not asking you to prove this inclusion. I'm just telling you to find a language which is unambiguous context-free but not deterministic context-free. But of course, in order to prove that certain things, some language is not deterministic context-free, you need some sophisticated tools like some pumping lemma for DCFL to just intuitively justify. Okay, so I should hand over to SK. What is happening? Okay, so if I consider these palindromes, And if you construct a grammar for this, that grammar has a unique parse tree against every palindrome, right? So you convince yourself. But why it is not deterministic, context free? What is an intuitive justification?
Sir, there is no good way of determining the middle of the string.
So any machine, any PDA that accepts this language will have to guess the center of the string and then validate the remaining portion. So it's not possible in a deterministic fashion, but then this is just an intuitive justification. Okay, so there are a couple of exercises on unambiguous grammar. So maybe you try this. Okay, so I think I should stop. I should have stopped much earlier, but anyway. So SK is willing to do some 1 or 2 maybe small exercises on Turing machine construction. So let her proceed.
Can you see my screen?
Yes, ma'am.
Okay, so just very small examples, a few more examples of Turing machine algorithms. The first one, you have to design a Turing machine to accept the language L that accepts all strings, that includes all strings over AB star, such that the number of A's is at most 2 times the number of B's. So you've seen this exercise in the context of context-free languages. Now, can you design a Turing machine algorithm? So, have you seen this exercise in when you were working on PDAs?
Yes, ma'am.
Okay, so
Ma'am, can we do the following? We take the input in the tape, and then for each B, we underline the B and underline the first 2 A's that are not underlined. And if there are some, if number of A's are being exhausted, then we are in the finals. We are in the reject state.
So you are moving from the left, you are looking at the first B and marking it.
Yes, ma'am.
Okay, and if you hit a blank, if you hit some elements and you hit a blank, then you are rejecting. Is that the first step? So if you don't come to a B, then what are you doing?
Ma'am, for all A's, so if there is no B, then we will always. So if there are no B's, then the string must be empty for this to be.
Right, right. So if there are no, before you look at before you come to a B, so one check that you have to do is whether this is an empty string or not. If it's an empty string, you accept. If it's not an empty string, then somehow you have to remember that. And if you don't come across any Bs, then you go to reject. This is one sanity check that you have to do and which you should be able to do in your finite control. And after that, I think what you're saying is look at the first unmarked B, mark it, and then go to the left again and search for two unmarked A's.
Yes, ma'am.
Okay. So just if you have a PDA for this language, right? You designed a PDA. So just think about how you can simulate that PDA where like how you can simulate the stack on a read write tape. You can also think of it that way. Anyway, I mean you gave one algorithm. If you can think of how to simulate a stack on a read write tape, there is just one small step that you have to work out. Otherwise, it should be fairly simple. Then you can basically show that CFGs or CFLs, any CFL is accepted, or any CFL is also recursively enumerable. So this is a simple exercise where you can try it, and the basic step is to see that a stack, or let me just write it in total, a PDA can be simulated by a Turing machine. Okay, I'll move to the next problem. So any questions regarding the first problem from anybody?
Ma'am, the stack can be simulated on the state, but in a PDA we are allowed to move from final states to non-final states and vice versa. But in the Turing machine, we need to stay in the final state and we need to stay in the reject state. So, how would we do that?
Yeah, so you can try and see how you can do that. That's the one
Okay.
step that you.
Okay, ma'am.
Okay, so next is you design a Turing machine to accept. Actually, that is one step, and another thing is in a Turing machine you always have to move to the left or right. But I guess yeah, these are the two things that you have to work out. But these are fairly simple. You should be able to. Okay, second is design a Turing machine to accept the language L2 that is of the form a to the n hash a to the m. So this hash is also part of input symbols, and you will accept this kind of strings if and only if the GCD nm is equal to 1, meaning n and m are co-prime. So, first of all, what algorithm do you usually use to determine the GCD of two numbers, two positive numbers?
The Euclidean algorithm.
Right. Can you tell me the steps of the Euclidean algorithm?
GCD of n comma 0 is n, and GCD of n comma m, where n is greater than or equal to m, is n comma n mod n.
N and GCD, otherwise GCD of n comma m is equal to GCD n comma m mod n, right?
Yes, ma'am.
Okay, so now can you simulate this algorithm? This is basically what you have to do, right? So you're starting with a tape where you have a to the n, then hash, and then a to the n, and you also have your finite control. So for now, assume that, okay, no, don't assume anything. Yeah, what will you do? First, you just check. Sanity check is the format of the string. Secondly, you check if m is equal to 0, in which case you will, if so, if n is equal to 1, then accept, otherwise reject. Okay, so now the third step is if m is not equal to 0. So now how will you do this? So basically in the a to the m portion, you have to reduce a to the m to a to the m mod n. This is the operation that you have to do, right?
Ma'am, we can take two directions according to if n is greater than m and m is greater than n.
Yeah.
And for instance, let us assume that n is greater than m is greater than m.
M is greater than n.
Yes, ma'am. And now we start marking off chunks of size n in the right part of the string.
Okay, so what do you mean by chunks?
Consecutive substrings, contiguous
Oh,
substrings.
so you're saying you're just marking off like so if you have a to the n, so you have m such a's, so you keep marking off n one after the other.
Yes, ma'am.
Okay.
And at some point we will mark an empty symbol. So when we mark an empty symbol, we just unmark the last chunk of n.
Yeah, so then I think you need a different kind of marking, right? Otherwise, how will you understand what is the last chunk? You need a different kind of marking for the last chunk, or for the
Yeah,
current chunk that is going on.
Okay, ma'am. Ma'am, I thought we can just we know the value of n, then we can just unmark the last n characters from the last empty symbol that is marked.
Last n characters, not last n characters, right? Last m minus n characters you have.
No, ma'am, I meant for, let's say if n is 4 and m is 5, then we will mark the first 4.
So you're okay. So you're saying that you mark n characters. Some of them may be blanks.
Yes, ma'am. Yes, ma'am.
Now, if at the end point it is blank, then you will again look at the a to the n portion and move backwards.
Yes, ma'am. Yes,
and mark anything that is that was marked. Sorry, unmark anything that was marked.
yes, ma'am.
Okay, yeah, that is also. So the suggestion here is keep marking chunks of a to the n. If end symbol is blank, then move back n steps. So this is you cannot count n, so you are matching a to the n again backwards. And keep marking, keep unmarking. Okay, now so now your a to the n, you have everything except the last m mod n elements unmarked. Now what do you do?
Ma'am, we copy all the unmarked symbols to the just after the hash separator.
How do you
Just
do that?
Ma'am, we can just take the first unmarked element and then move left and unmark the leftmost marked element and so on.
So you have to basically move a to the m mod n to just after hash. And how do you do this? So so this a to the m mod n at the end, just for safekeeping, you mark differently. Now keep moving up to hash and unmark is as matched with newly marked is of a to the m mod n at the end. Okay. So once you do this, after that your a to the m will have first m mod n a's are unmarked, and after that all a's are marked in different ways. So now you just make a pass and delete these a's. These marked a's, make a pass from the right and delete these marked a's. Okay, and you made an assumption that m is greater than or equal to n. So if m is less than or equal to n, then what do you do?
We can just find so if m is less than n, then we can count the first m characters in a, and then the m plus 1th a we replace by a dollar symbol, and then we replace the hash symbol by an a, and then replace the dollar symbol by hash. So we will get a to the power n, a to the power m, a to the power m hash a to the power n, which is the reverse tree.
Did not understand properly. So if, suppose m is less than n, what are you doing?
Ma'am, we replace the m plus 1th a in the left hand side by
M
a dollar
plus, so you are replacing m plus 1th cell. No, m plus 1th a in a to the n side.
Yes, ma'am.
Oh, okay. So basically you're saying do the same thing on a to the n.
My objective was to reverse the string so that it is of the form m is greater than or equal to n.
Okay, so I have one question. First of all, how are you checking whether n is greater than or equal to m or not? You are doing some matching.
Yes, ma'am.
Okay, so now suppose n is less than or equal to n, less than n, then you are reversing the string.
Yes, ma'am. But since it is only of the form a to the power n, b to the power a to the power n hash a to the power m, then we can just switch the symbol, switch the position for the hash symbol, and it would be sufficient.
Okay. So this you are doing as following. So the position of hash has to be corrected. And for this to be, because of the structure of the string, the position has to be corrected, and because of that you mark off the first m a's, and in the just before that, just after that, look at the m plus 1th position, put in hash over there, and in place of the hash you write another a, and that is how you will come back to this case and repeat. Okay, any questions? I think that's all the time we have. I've overshot. So there's just one last question I wanted to try. You can do it on your own. Similar to all the strategies that you've been working on, you have to design a Turing machine for accepting the language A to the N, where N is a power of 2. Again, there has to be some matching that will happen, but try this exercise out. N has to be a power of 2, and you need to accept all such strings. Okay, I will end the meeting. Thank you.
Thank you, ma'am.